Welcome to Chapter 5 on matrix transformations and factorizations. The primary interest is on factorizations of matrices. We encountered some matrix factoring in Chapter 3, matrix decomposition it's also called. We diagonalized matrices, for example. In this chapter, we'll introduce three new factorizations. The LU and the LR and the LDU factorization of a general matrix, N by M matrix, the QR factorization of a general matrix, and the Cholesky factorization of a non-negative definite matrix. So no conditions on these first two and a bit of a condition on the non-negative definite condition for the third type of factorization. Maybe a global comment about factorization, or why do you want to write a matrix in a different form? Well, we've seen that already. We diagonalize matrices because raising a matrix to a power without some simplification first or some modification is just nightmarish because of the row times column, the awesome amount of arithmetic that has to be done, which can be streamlined if you'll diagonalize the matrix. Then raising matrices to powers is a relative piece of cake. In section 5.1, do consider transformations and transformations by orthogonal matrices. Now, in linear algebra, you deal with linear transformations, and they're always represented by matrices. All that holds, of course. We're looking at particular kind of transformations, this time for an orthogonal matrix. We've already encountered some of this in Chapter 3. We saw that if we take an orthogonal matrix Q, one for which, for example, Q transpose times Q equals the identity, so Q transpose is Q inverse. We defined it as a matrix with orthonormal columns or orthonormal rows, depending on whether it was square or not. We saw then in Chapter 3 that if we take a matrix and take its L2 norm, its Euclidean norm, Q times X, that vector has an L2 norm that's equal to the L2 norm of X. So what happens then is if we were to define a transformation using an orthogonal matrix, then that transformation would preserve links with respect to this norm. So we get the usual Euclidean norm is preserved if I take a vector X and multiply it by an orthogonal matrix Q. Turns out links aren't the only things that are preserved. If we have an orthogonal matrix, angles are preserved as well. If Q is an orthogonal matrix and X and Y are vectors of appropriate size, if we take the inner product of Q times X with Q times Y, okay, we can write that inner product as a matrix product by transposing the first vector. Remember the default, the vectors are, unless otherwise stated, treated as column vectors. So here we've got a row vector times a column vector. So that's just your row times column thing. That's how we can write dot products as matrix products. Technically, we get a 1-by-1 matrix, but we treat it as a scalar. We've been through this. Transposing that first product, QX, gives us X transpose Q transpose. Hey, now we've got Q transpose Q. You know that's an identity matrix. If Q is orthogonal, we drop that and get X transpose Y, which is the inner product of X with Y. So inner products are also preserved under a transformation defined as multiplication by an orthogonal matrix Q. If inner products are preserved, then angles are preserved. We had defined angles between vectors X and Y to be the arc cosine of the inner product of X and Y divided by the norm, the L2 norm, the Euclidean norm of X and Y. So if we wanted to find the angle between Q of X and Q of Y, we do the same type of thing. We observed upstairs that, hey, the norm of QX is the same as the norm of X. The norm of QY is the same as the norm of Y because orthogonal transformations right here, preserve L2 norms. And we just saw the inner products are preserved as well. So we can replace the QX, QY inner product with an inner product of X and Y. And that's the angle, by definition, between vector X and vector Y. So multiplication by an orthogonal transformation preserves angles between vectors as well. An angle preserving transformation in analysis, really probably complex analysis, is often called a conformal mapping, though that terminology is not used here. But we see that using orthogonal matrices gives us preservation of links and preservation of angles as relates to vectors. And we'll give that a name in section 5.2. We'll call that an isometry. And like this section, that completes section 5.1. The other sections are a little meatier, and we'll have more material in some of the future sections in chapter 5. Have a nice day. I'll see you in section 5.2.